Hello, folks. How we doing? We are on, I guess, lesson three in our series. So far we've talked about 8 different tests, and the 8 different tests we were making the assumption, or we were using the fact that all the terms were positive. The 8 tests, just to kind of write them out. I guess we could spend a few seconds writing them all out. Doesn't hurt, right? So we could write them all out. The first test that we talked about was the divergence test. And that's when we saw that we wanted to make sure that the series was approaching 0 to have a chance at convergence. We looked at infinite geometric series. We did a p-test. We did a comparison test. We did the limit comparison test. Then we did the integral test. We did the ratio test. And we did the root test. And when we did these tests, we were assuming that all the terms were positive. That meant every term in the sequence was positive, wasn't changing signs. We are now going to change gears, and we're going to talk about a different type of series that kind of goes back and forth. And the way we're going to write this back and forth is we're going to make sure that there's some element that is turning from positive to negative and positive to negative back and forth. And the easiest way to kind of write this series is to write it like this. And I'm going to use +1 just because we're going to start at 1 here. You don't really need a +1 there to alternate. But we're going to write it like this, where this part here just shows that it's alternating signs. And therefore, we're going to make the assumption that this term here is kind of always positive. And if that's the case, we have what we're going to call an alternating series. So you may be asking, okay, what's the big deal? What's the big deal about an alternating series? Well, let me give you an example of one first. Let me give you an example of an alternating series. This alternating series is called the alternating harmonic series, because the harmonic series is this series with all pluses. The alternating harmonic series looks like this. Now, as we discussed earlier, we did this way back when we did the p-series test. The harmonic series, the one that does not alternate, definitely diverges. We proved that with the integrals. We proved that by showing the fact that the integral is going to infinity. But this alternating series, let's think about this, right? Let's imagine that we're going out, we're starting off with 1. So we're going to add 1. So imagine we're starting here, we're adding 1. And then what we're going to do is we're going to subtract a half. Now we're going to go back and we're going to add a third. Looks right about there. Then we're going to subtract a fourth. And we're going to add a fifth. And subtract a sixth. And what we're seeing here is that there's some line here. There's some kind of line somewhere in here. I don't know where it is exactly, but it's going to be somewhere in here that it's approaching. There is some sum that is being approached. Now, that sum is some number that if you kept on adding, you went back and added a 7th and subtracted an 8th and added a 9th and subtracted 1/10. If you kept on adding and you kept on going out and out and out, you would approach some number in the middle. So it is converging upon some sum. It's not going off to infinity, right? It's getting somewhere. But the fact is, it's really alternating, and that's the reason why, right? It's going out to 1, then back to 1/2, down a half, then up a third, then down a fourth. The reason why it's converging upon some sum is that it's alternating, and every single time it's kind of getting smaller and smaller and smaller. Each term is getting closer and closer to 0, so it's approaching some number. And this alternating series tells you that, hey, look, this series, because it's alternating, it's actually converging upon some number. So we're going to talk about series that are alternating, and we're going to talk about the conditions for when it actually converges and when it doesn't. So we're going to say that a series that is alternating, we're going to talk about, can kind of converge because it's alternating, not because it actually, it's approaching zero, absolutely, but because it's alternating, it's going back and forth, it's actually going to approach some number. And we're going to call that conditionally converging. We're going to say that an alternating series converges conditionally when the following are true. And again, what we're talking about when we're talking about an alternating series is something where the alternating element right here is alternating. Therefore, it goes from positive to negative, positive to negative. So there's some alternating element here. Okay. So the three conditions are what? One, the sign changes every term. What that means is that it can't be plus plus minus minus or minus plus minus plus 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 minus minus. It has to always be plus minus or minus plus minus plus. Okay, so it has to change every term. Two, that each term, the absolute value of each term, well, I guess I should kind of point to the a sub n here, because here we're talking about how the a sub n is always positive because we have the alternating element in front. So each term is less than the previous term for some value n0 and above. And what does that mean? Well, it means that there has to be some place where it starts to get smaller. I mean, a series could look like this. I mean, here's an example down here in the bottom left. I could say, hey, look at this, right, folks? Look at that. It's starting to get bigger and bigger. Each term is getting smaller. It's getting larger. But then it starts to turn around for some reason. I don't know. I can't come up with a quick formula, but it starts to turn around. And then it goes like this. And now suddenly it's getting smaller. And the absolute value every term is getting smaller. And if it were to do something like this, where you may say in the beginning here, it wasn't really getting smaller, right? But after this point, kind of after this point on, starting at some n0, it started getting smaller. And when I mean by smaller, I mean the absolute value of each term. 3 is smaller than 5. 1 is smaller than 3. 1/3 is smaller than 1. It starts getting smaller and smaller, and the absolute value of each term is getting smaller and smaller. If that's happening, then, okay, you have a chance for a conditional convergence. Less. And this is kind of important because we talked about this way back when we did the divergence test, that in order for this to converge, they have to be getting close to 0. The terms have to approach 0. If the terms aren't approaching 0, they're not going to get a sum. I mean, a perfect example would be this, right? You may say, well, what about this? Well, that's alternating, right? And yeah, fine, you might say to yourself, well, yeah, that's not getting smaller and smaller, so maybe I could do something like this. 13 over 12 minus 14 over 13 plus... I think that's getting smaller every term, right? So this one here, right? So fine, forget that one because that doesn't meet condition number 2. But look at this. This guy meets condition number 1. It meets condition number 2, but it's not going to converge conditionally because it does not meet condition number 3, right? This last guy doesn't meet condition number 3, and therefore it's not going to converge conditionally. So these 3 conditions up here, right? I just give you a couple examples down here. This guy, for the record, this guy looks like it would converge conditionally because it's getting smaller and smaller. It looks like it's getting closer to 0. We kept on going out. So this one does look like it would, conditionally converge. So A alternating series is called, a conditional converging if it meets all these requirements. Now, alternating series, you would say, why do we have this conditional convergence? Well, there's another thing where it could be absolutely converging as well. Just because a series is alternating doesn't mean that it's only converging because it's alternating. A series might actually be converging even if it wasn't alternating.